In the earlier class, I have discussed about the two-step methodology of Engle-Granger to find out the cointegration between two variable yt and xt, and in this class I will discuss basically what is the problem that we have of applying Engle-Granger methodology. Now then I will discuss the problem of getting cointegrating relationship for a general case where you have k number of explanatory variables in the system, and this is basically done by Johansen approach, and we will explain Johansen procedure for estimating cointegrating relationship, and I also explain the test procedure, that is how do you perform hypothesis testing in this approach. Now, we have discussed Engle-Granger methodology of two-step cointegration. Now, let me discuss a little bit about the problem with the Engle-Granger model methodology. This method suffers from number of problems. First of all, in this case, first treat yt as a dependent variable and xt as an explanatory variable and perform the regression and obtain the residual, and then test whether the residual follows I0 or not. Alternatively, we can take xt as a dependent variable and can express xt as a function of yt and can perform the least square and obtain the residual and can see whether the residual of regression of xt on yt is I0 or not. So, in many cases we get contradicting conclusion based on regression of yt on xt at the same time from the regression of xt on yt. So, if we get two contradicting result, one from the regression of yt on xt and the other from regression of xt on yt, then we fail to conclude anything regarding the existence of cointegration applying this methodology. And this problem is tackled by the Johansen approach that I will consider in a minute. And secondly, we cannot perform any hypothesis test about from the actual cointegrating relationship based on stage 1. This problem too is also tackled by Johansen approach. So, in the next step, I will basically explain the existence of finding cointegrating relationship from using k variable case, that is if you have k number of explanatory variable and one dependent variable, then how to get the existence of cointegrating relationship. So, this is done by Johansen test and Johansen's methodology, and in order to apply this methodology, first we have to write the system in var form. In our earlier classes, we have also discussed how do you write the var system, that is vector autoregressive system. Now, let us write the system as yt as a function of yt minus 1, yt minus 2 up to y2 minus k, and we have also seen that if you use two variable cases, and then we can generate an error correction mechanism from the relationship. Similarly, for the general case from the var, we can also get an vector error correction mechanism is written as pi yt minus k up to pi k minus 1, and along with the disturbance term ut, and where you are taking the differences yt minus k to up to yt k minus 1, where pi matrix as follows, and pi is a long run coefficient matrix, and since at all delta yt minus 1 it should follow 0. Now, in order to apply Johansen test, we need to carry out or need to know some properties about the eigenvalue of any square matrix A. First of all, the sum of the eigenvalue is the trace, the product of the eigenvalue is the determinant, and the number of non-zero eigenvalue is the rank. So, returning to the Johansen test, the vector error correction mechanism is represented from the var as like this, where changes in yt is expressed as a function of the past delta yt's as well as the coefficient matrix delta yt minus 1. So, the pi matrix is analyzing pi matrix is crucial for Johansen test. The test for cointegrating relationship between y is calculated by looking at the rank of the pi matrix via its eigenvalue. Now, rank of a matrix is equal to number of its characteristics roots eigenvalue that are different from 0. And let the eigenvalue is denoted as lambda I, and we can order the eigenvalues lambda 1 greater than or equal to lambda 2 up to lambda g, and if the variable are not co-integrated, the rank of pi will not be significantly different from 0, so that all the eigenvalues are 0. So, if we find that all the lambda i's are 0, then log of 1 minus lambda i's are also 0. If lambda has the roots, they must be less than 1 in absolute value. So, if we find that rank of the pi matrix is 1, then 1 minus lambda I will be negative and log of 1 minus lambda I is equal to 0. If the eigenvalue I is non-zero, then log of 1 minus lambda I is less than 0 for all I greater than or equal to 1. Now, using this test, using this property, the test statistics are for Johansen test as follows. You have to calculate lambda trace and lambda max. Lambda trace and lambda max are the two critical variables which are used in order to find the rank of the matrix and Johansen test. Well, lambda is the estimated value of the ith order eigenvalue from the matrix pi. Lambda test the null hypothesis that number of co-integrating vector is less than or equal to r against the unspecified alternative, and lambda trace equal to 0 when all the lambda I equal to 0, so that it is a joint test. And lambda max test the null hypothesis that number of co-integrating vector r against the alternative hypothesis r plus 1. So, Johansen and Julius provided the critical value of the two statistics, and distribution of the test statistics is non-standard. Now, the critical values depend on the value of g minus r, the number of non-stationary component, where a constant and or trend are included in the regression. So, if the statistics is greater than the critical value from Johansen table, reject the null hypothesis that there are r number of co-integrating vector in favor of the alternative that there are more than r co-integrating vector. We perform the test sequentially. First, we test whether r equal to 0, 1, etc. up to g minus 1. So, that hypothesis for lambda max r, h naught r equal to 0 versus h 1 r lying r is greater than or equal to 0 but less than 1, and r equal to 1 versus r h 1 r lying between g, and r equal to 2 versus h rank of the matrix or co-integrating relationship 2 lying between r 2 is less than r or less than g. So, first what we do, we test whether rank is 0 versus rank is 1 versus rank is 2, like that, and finally we test for whether the rank of the matrix is r equal to g or not. So, we keep on increasing the value of r until we have no longer reject the null hypothesis, and test statistics to test the hypothesis are this, where the test statistics follow a chi-square degrees of freedom with m number of. So, lambda I star the characteristic roots of the restricted model and lambda I at the characteristic roots of the unrestricted model. So, here you find that two components, one is lambda I and other is lambda I star, that is lambda I star is the characteristic roots of the restricted model and lambda I are the characteristic roots of the unrestricted model. So, r is the number of non-zero characteristic roots in the restricted model and m is the number of restriction. So, this is how we go for testing in Johansen case. In Johansen case, we basically test what is the rank of the matrix, and we try to find the rank of the matrix. If the rank of the matrix is r, then we claim that there are r number of co-integrating vector, and as a result there exists r number of co-integrating relationship. Now, if the variables are co-integrated, that is, if a long run equilibrium exists among the set of variables that share similar non-stationary property, regression involving level of the variable can proceed without generating spurious results. Now, cointegrating factors are considerable interest since they determine I0 relation that hold between the variables which are individually non-stationary. Essentially, variables are cointegrated when long run relationship is obtained from a set of variables that share the same non-stationary property. Hence, the intuition behind the cointegration is that it allows capturing the equilibrium relationship detected by the economic theory between non-stationary variable within a stationary model. So, the basic idea behind use of the cointegrating relationship is that it helps to find out the long run relationship between the model. Now, a search is made for linear combination of such variable such that their combination is stationary, and if such a stationary combination exists, then the variable are said to be cointegrated, meaning that even though they are individually not stationary, they are bound to be an equilibrium relationship. So, the basic idea of using cointegrating relationship is that we can combine two or more different non-stationary relationship into a stationary relationship such that you can claim that equilibrium relationship exists between the variable that you have used. Now, according to Lütkefold 2004, you can comment that occasionally it is convenient to consider the system with both I1 and I0 variable. Thereby, the concept of cointegration is extended by calling any linear combination, that is I0, a cointegrating relationship, though this terminology is not the spirit of the original definition, because it can happen that a linear combination of I0 variable is called a cointegrating relationship. So, what we do? We basically try to combine two different non-stationary relationship into a stationary relationship I0 variable by forming a cointegrating relationship. In this class, I have started with the limitation of Engle-Granger two-step methodology of finding cointegrating relationship. Then I discuss how do you find cointegrating relationship for a general k variable model. For that, we basically use Johansen method of cointegration. I explain what do you mean, how do you test for cointegration using Johansen approach. One advantage of Johansen approach is that you can test for hypothesis using this framework. I have also explained how do you actually test for existence of number of restrictions into the model, and then basically explain the idea of having cointegrating relationship, what actually we mean of having a cointegrating relationship.